Maybe I should start this one with hot stuff, baby. No, I won't do that. No, I won't do that to you. Talk about thermionic emission. Thermionic emission is electrons jumping from the surface of a hot metal, leaving the surface of a hot metal, well, because it's hot. The reason for its energy, sort of a signature, etc., you do not need to know. You just need to know that it happens. Thermionic emission is where you simply heat up a metal and some of the electrons will leave. Now, they don't go very far. They stay in a cloud very close to the surface of the metal, but they are there. The other thing to remind you is that G. Stoney named the electron. He gave the electron its name. Why is that important? Because G. Stoney was born in Ireland. He was Irish in every sense of the word. And let's face it, we have to make sure people like that are remembered. So, why is thermionic emission important? Because all cathode ray tubes, X-ray tubes, old television sets, oscilloscopes, quite a lot of other equipment is based on this idea. In order for you to get the electrons to accelerate and hit something, you first have to get them off of the cathode. So you heat up the cathode, and by thermionic emission, the electrons leave the cathode. Only once they've left, only once the hot cathode has admitted the electron, can you then accelerate the electron across a very high voltage field. High voltage field, high voltage field. Yes, it's important. A very high voltage field to accelerate the electron, to form a stream of electrons towards the anode. And that's what happens. So first the heat makes them jump off, and then they are accelerated towards the anode by the high voltage field. Now, this is such an important part of physics that we've invented a unit just for it. If an electron is accelerated through a field of just 1 volt, so there's a 1 volt difference in potential between the cathode and the anode, a 1 volt potential difference we call it, then it's got an energy gain of 1 electron volt. So it's a completely new unit just for this. Now, we use it an awful lot. We use the unit a lot because we use this kind of thing an awful lot. We accelerate particles an awful lot. So when we're passing particles through fields, we use this energy unit of electron volts. But we also have to be able to convert this energy unit into joules. So 1 electron volt gained when you go from 1 volt, 2,000 electron volts gained if you go through a 2,000 volt field. Guess how many you gain if you go through a 4,000 volt field? Yes, it's 4,000 electron volts. Yes, this is tough stuff, isn't it? This is why you did physics, to get the really challenging problems. Okay, now we have to, of course, be able to convert this into joules, because in all other branches of physics, we use the energy of joules rather than the energy of electron volts. So here is the joules calculated. And what do? Well, it's dead simple. We multiply the voltage by the charge on the electron. Do you have to remember the charge on the electron? No, it's in the book like everything else. If you multiply the charge on the electron by the voltage, you get the number of joules. Now, it's really not difficult to remember it, because if it's written EV, that is essentially the formula. This is your voltage, which is written down, and this is the charge on the electron, which is always called E. I'll get that arrow a little bit better. There you go. So, I'm a terrible doodler. Anyway, so you are basically looking at the formula when you're looking at the units. Electron volts is the voltage, the number, times the charge on the electron, 1.6 times 10 to the minus 9, and that's in coulombs, which is the unit of charge we will meet throughout the course. Now, if you want to then work out how much velocity is gained, because the electron on this side is at 0 velocity, what's the velocity over here? Well, that's quite simple. We've just worked out the energy gained, that's it, by multiplying the voltage by the charge on the electron. Now we use this formula, the formula for kinetic energy, a half mv squared, which you vaguely will remember perhaps from junior cert, and if you don't, guess where you can find it. Absolutely, right there, right smack in that book that I've been talking about. The m is the mass of the electron. It's on a different page, but the same book. You put the mass in. You've got the energy, because that's the kinetic energy. You see, because an electron can only hold kinetic energy. It cannot hold any other form of energy. So you've got the kinetic energy. You have got the whole energy of the electron. So the energy equals a half mv squared. You've got the m. The only thing missing is the v. So you work out the v squared, you square root it, you get the v. Now, of course, that's quite a fast velocity. That's 10% of the speed of light. But there's all sorts of relativistic effects come into as you increase the voltage. You can't actually make the electron go faster than the speed of light. So we tend to look at questions which don't do that. Don't bring it even close. 10% of the speed of light, that's not going to have a huge relativistic effect. 70% of the speed of light, whoa, that's going to have huge changes. It's not going to go anywhere near 70%. A lot of the energy is going to be used up in other ways. So here is the device which mostly uses this. You see, there you are. This is the cathode. Here we have it, the cathode. Let's change colour because the black's already there. What do you reckon? Red? Okay, we'll go for red. Here is the cathode. As you can see, it's heated. It gets hot. It actually gets hot. You can see it. It's like a light bulb in the back of the tube. Glows. And the whole tube gets hot because of it. And that glow is so electrons will jump off of the cathode by thermionic emission. Thermionic. No, that's not it. I don't know. Anyway, it's spelt correct at the beginning. You have to look back. Thermionic emission. They then get accelerated towards the anode. But the anode's got a hole in it. And the electrons go straight through. And they get focused onto the screen. So they can go that way or that way. And change where they make the spot by these deflecting plates. The horizontal and the vertical deflecting plates. These ones deflect it horizontally, basically left and right. And the vertical plates, these ones here, deflect it up and down. And obviously it's difficult to do left and right because it's a flat image. But, you know, yeah. And then they hit a phosphor coating screen, which might be phosphor coating, it might be zinc sulfide. But basically, you get the energy of the electron, its kinetic energy, gets turned into light as it reacts with a chemical which is coated on the surface of the screen. And that's a cathode ray tube. I should point out all these little connections, all to do with this. Some of them are the power supply, which power the heater, and some of them power the deflecting plates. But essentially, that's a cathode ray tube. And it's still in oscilloscopes. You still see it very much this is essentially how an X-ray tube works. So we'll have to work on that a little bit later when we do waves. So that's the whole subject, except for the question, which of course you will have to complete. Good luck.